After a user locks their collateral and then borrow DAI from the MakerDao stablecoin system, their DAI will accrue interest rate. This interest rate is called stability fee. When they repay the DAI to unlock their collateral, they'll have to pay the borrowed amount plus this interest. The way that the MakerDao stablecoin system keeps track of the interest for every user is by a single state variable called rate accumulator. This state variable is unique for each collateral. The function that updates this rate accumulator for each collateral is called the function fold inside the contract vat. So in this video, we'll rewrite this function. I'll copy this code, and then inside my code editor, I have the file CDP engine open. I'll paste it inside here. And before I proceed, I'm gonna type forge fmt to format the code. Okay, and then going back. So we're gonna rewrite the function fold. This is a function that can only be called by an authorized account to update the rate accumulator for a collateral. This first input, I, will be the identifier for the collateral. Let's rename this to call_type. The next input is an address called U. This is an address that will receive the interest that the borrowers of DAI will have to repay. So the borrowers of DAI will repay the MakerDao stablecoin system, and this user U will receive this interest. Later on in another contract, we'll see that this user is set to the val contract. Val contract is a contract that both receives the profit and the loss of the MakerDao stablecoin system. The profit will come from the stability fee that the users have to repay, and the loss will come from an under-collateralized loan where the collateral could not repay the full amount of debt. Since this is an address that's going to receive the profit of DAI, but inside our code, we rename DAI as coin. Let's rename this as coin DST, coin destination. Okay, and the last input is an int 256 called rate. So this is an input that has to do something with the rate accumulator. Later on, when we dig through this part of the code, we'll see that this rate is actually delta rate, change in the rate accumulator. So I'll rename this to delta rate. Next, it has a modifier called auth, which means that only an authorized account will be able to call this function. And then inside the body of the function, it requires that lib is equal to true. Let's use the modifier from the circuit breaker called not stop, which basically does the same thing. Okay, next we have the IOK. We rename this as collateral, and the same for the state variable. This is collaterals. Okay, and then let's rename this storage IOK as col. The first part of the code gets the information stored in the struct called collaterals. One of the data that is stored in the struct is the rate accumulator, the current value of rate accumulator. Inside our code, we rename this as rate ACC for rate accumulator. Okay, and then I see a rate over here. Let's change this to delta rate and delta rate over here as well. Okay, next I see a lot of internal functions called add, mul, and add. All of the math library, I moved it over to library math.sol. So inside this contract, we'll call the function math.add and math.mul, and then over here math.add, and then over here math.add. Now the reason why we're calling math.add and math.mul is to handle the case of adding UN256 with int256. The rate accumulator is a data type which is UN256. However, delta rate is int256. And the same goes over here. Call.art is UN256 and delta rate is again int256. So that is why we're calling a library function to handle this case of adding two numbers of different data type. Let me explain what's going on over here so far. First, it updates the rate accumulator by calling math.add. So add to the current value of rate accumulator, delta rate. Since delta rate is int256, this can represent both positive and negative number. Next, it multiplies call.art with delta rate. Let's check back to see what we renamed this as. So over here, it says art is the total normalized debt, and we renamed it as debt. So this will represent the total normalized debt that was borrowed using this collateral. And then we multiply by the delta rate to get a number called RAD, which is int256. So what's going on over here? We can start to see what's going on over here, what this state variable represents, by looking at the next line of code. Next line of code says DAI, coin destination is equal to add the current DAI for coin destination with the amount rad. So it looks like this rad represents some kind of amount of coin to either add or remove from coin destination. So let's rename this rad as delta coin, and let's rename this DAI state variable. We renamed it as coin. Okay, and then we have a rad over here, so delta coin. In the last line, it updates the system det by adding delta coin. Inside our code, we rename this as sys det. Okay, so that completes the code, but let me explain a little bit further about how this delta coin is derived. So we know that the current total det is calculated by multiplying col.rateACC by the actual det, col.det. This will represent, let's say, old total det. This will represent the total debt that was borrowed using this type of collateral, and this includes the amount of interest rate that must be repaid. So that is old total debt. And then we do this update over here. So the new total debt will be col.rate accumulator plus this delta debt, delta rate, and then multiply by col debt. And now if we want to find out the difference between the new total debt and the old total debt, we can simply subtract the old total debt from the new total debt. So let me write this as delta coin is equal to new total debt minus old total debt. But from the two equations above, we can simplify this expression. New total debt is this over here, and then here's the old total debt. So we minus old total debt from new total debt. And notice that from the top, we have col.rate accumulator multiplied by col debt. And on the bottom, we're minusing col.rate accumulator by col debt. So this term and this term will cancel out, and we're left with delta rate multiplied by col.debt. What we end up with is that delta coin can be calculated by multiplying delta rate times col.debt. And this is the code that we see over here. Okay, so that completes the function fold. Let's try compiling this contract. Inside my terminal, I'll type forge build. Okay, and our contract compiled.